Okay, so without further ado, can I ask the first presentation to come up, which is Ian Griffiths and Sheena Wilson on transforming a national institution, a case study in bringing together OR practice and engineering expertise to improve the waterways of England and Wales.
Hello. We've actually shortened the title, made it a little bit snappier, but we're going to be talking about the Canal and River Trust work we've been doing. Now, she's going to start by just talking about the requirements and the needs, and then I'll talk about how we've approached the journey we've gone on, and then the most important part, Sheena will talk about so what, the impact. So I'll hand over now.
Good afternoon. So who are Canal and River Trust and why are we doing this? Canal and River Trust were formerly British Waterways. We were the last of the Quangos to be disbanded by the government in 2012 and performed into a charity with the support of a 15-year government grant. We are responsible for an eclectic range of assets, as you can see behind me, ranging from bridges to boat lifts to pumping stations to mileposts to historic assets such as pillboxes and heritage cranes, from locks to reservoirs to visitor centres, and from aqueducts to weirs. After British Rail and the Church of England, we are the third biggest landowner of heritage assets. Doing all of this while looking after the environment with the bats and the voles getting in the way and an awful lot of vegetation, so I included some green in the pictures behind me. As well as hosting over 4,000 boats, we are used by businesses for water cooling and fire protection systems, and if any of you have had a glass of water supplied by Bristol Water, then it will have travelled by one of our canals, which may be a nice thought or not, depending on how you feel. Already we know that the waterways are contributing to the economic, social, environmental and cultural well-being of the nation. Our waterways and museums attract in excess of 4 million regular users, and this is everybody from walkers to fishermen to cyclists to commuters to boaters and many more. Just another fact for you, there's more canals in Birmingham than there are in Venice. But to support all this, we need an attractive but reliable, sustainable and safe environment for the public. So why did we need OR and decisionLab to help us? The negotiation with government became the trust. Came with a number of KPIs to maintain a grant for 15 years, but there are no guarantees past that 15 years that we will get any funding. And part of our success in getting funding is proving that we are managing the waterways in the correct way. So obviously we don't want the declining waterways, we want the living waterways, transform places and enrich lives. My boss, Richard, who's mentioned on the paper, joined us in 2015 and I've had a background in asset management from working in the electricity industry. We, as a ex-government funded organisation, had been very much working in a reactive way and inspecting everything rather than worrying about maintaining it because we never had enough money. Richard came with a different perspective and is leading us through this change, which will hopefully see us in the next 10 years lead to a positive renegotiation with government. So how do we get from a reactive maintenance repair focused organisation to a customer focused one that demonstrates our excellent stewardship of the waterways? The bringing together of decisionLab, OR best practice and Canal and River Trust's engineering expertise is the first step in this process.
Okay, I wouldn't mind just kind of backing up, because I remember the kick-off meeting where we had a presentation like this of all the assets and been incredibly impressed by the huge range of assets the Trust has, and also really quite scared because they wanted an approach, a modelling approach to allow them to understand the condition of their assets and predict the condition of their assets, and they wanted it to be consistent, the same approach to all of these huge range of assets. And the other challenge was they didn't have a lot of quantitative data in terms of condition information. They had a lot of qualitative information, and they also didn't have much data on failures, mainly because they're really good at engineers and fixing things. So that was a problem, but a really good problem, I guess. But it was a challenge to us. But what they did have was this. a huge amount of expertise, engineering knowledge and deep expertise in their assets, in their infrastructure, and understanding what goes wrong and how to fix things. And we realized very early on, that's what we're going to utilize and exploit, because we didn't know a lot about canals. They didn't know a lot about modeling, so we're going to have to work together to solve this problem. And we started with a pilot phase, sort of sensibly, and we chose together 3 very different asset classes. They are the culverts, which are the tunnels that go underneath a canal to take water through. I didn't actually know what a culvert was until the project started. Brick arch bridges and lock gates. Very different assets. Like a lock gate typically will last about 25 years, a wooden timber gate. Brick arch bridges, pretty much indefinite. They have Roman bridges in the portfolio. Culverts typically last about 300-400 years, a huge range in these. And I also want to show these photos, because these are the kind of asset leads which were selected. There was Chris, Jim, and Tony that we worked with on sort of every 2 to 4 weeks. We'd have meetings together, workshops, to go through this process, understanding their model. So these guys are absolutely vital to what we did. Now, sensibly, we looked at what else was out there. Now, we looked at something from the Highway Agency, they had something called the Bridge Condition Index, which became later the Condition Performance Indicator. Seemed like an ideal approach to use. Unfortunately, the results were terrible. It just didn't match what the experts were telling us in terms of the condition. So it's quite surprising. We have a background in working with the sort of electricity companies. And so we're very familiar with a methodology called Kenai, which is developed by the power distribution companies plus Ofgem. But the issue there is that's a very data-driven approach. They've basically taken millions and millions of assets and done an empirical model of those, which then modified. That's just not applicable here because we don't have that sort of data. So what we had to do was really develop our own approach collectively together. And what we needed was the experts, the subject matter experts, to educate us modelers into these assets. And then together, we had to kind of work out what's the most important information and how do we gather that information as efficiently as possible. And then us modelers would implement a model, and then we'd sort of verify and validate it, going back, checking the assumptions. But this was not linear. This was very much, the diagram shows, a kind of a circle which we go around almost on these 2-3 weekly basis. And there's a lot of head scratching at these meetings as we try to understand things. A lot of head scratching for us between the meetings, and I'm sure for the asset leads too. It was some quite challenging meetings, but always really very enjoyable. So the kind of asset lead had to think about their asset, and they had to think about the components that make up their asset. This is a culvert, so you can see the different breakdown. And they had to think about how can these components fail? What are the different failure modes? And what are the different failure rates for all those components? And the consequences, what happens when they fail? And what are the interventions they can do before failure at different stages? And then the costs both of consequences and intervention. So that's the information they're gathering on large numbers of assets. Something we did take from the highway agency's work was a matrix they used for severity extent for converting from the qualitative assessment to a number to go into the modeling. And they used this severity extent of, so you talk about how bad a problem is and what coverage it is. So this is, although these descriptions are qualitative, it's a bit more objective than what we had before, which was just A to E. That was a single record with some notes of variable quality. So it's a bit more objective, and so it gets us on a number, which we can use in the modeling. We didn't just use severity extent, we also use variability and maintenance depending on the assets, and you can also do a double data-driven approach, which we've actually done for another client. Then we need to think, well, that starts to get us in condition now, but we will need to think about the future. How do these assets degrade? And we wanted to think about the degradation rates, and we had the concept of simplifying it just for a different component. How quickly do they degrade, having a normal, fastest rate of degradation, and then speaking to the asset leads about what are the factors that affect this most, so that we could use them to assign for every component of every asset, which is its failure curve. So quite a practical way of getting on that. And then we also need to think about the criticality, how important each component of each asset is into the scheme of things. This is really important when you start doing cross-asset type optimization, which we will do. We've done this a lot in electricity, it's done in other sectors. A good way of doing it is to convert it all to a cost of failure and a monetized cost of failure. And you think about the repair costs, the safety costs, because you can have fatalities, injuries, environmental costs. So if you lose the water in a canal, that will cause a lot of damage. You'll also lose all the fish, which is there's a cost there. So there's different environmental costs than you might imagine. The disruption, the boaters can no longer use their boats and you can no longer walk along the canal. Cars around bridges will have to go around, so we're trying to capture that. And then the utility is quite unusual. And there's a lot of infrastructure from utility companies going through the network, going across bridges. And if the culvert falls down, there's a kind of a virgin cable media going through and that's lost, the trust has to pay them compensation. So we can cost all that together. The actual modeling approach we use, we went back to classical reliability theory. So this is the bathtub curve of failure. So you can see there, we're particularly interested in the yellow on the wear-out failure because the interventions can't do a lot about infant mortality or even the constant sort of random failures. But we can do something about the wear-out. So we're using the viable distribution, which is very common in survivability theory, reliability theory. So it's kind of, there's the equation for the failure rate. We actually use the CDF, the cumulative distribution function, as our kind of common measure for an asset health, because we could use it for both the population, what percentage of assets have failed, and we could start to discuss with the engineer how many do you expect to fail over a certain period of time, and speak in languages they could understand, and failures, and get on the curve. But you can also then use that for an individual asset. Given it hasn't failed yet, what's the probability going to fail next year? And you can kind of go back to the failure rate. So that's our common kind of currency within the modeling. And then we stick it all together. So we're starting up at the top left, where this is our severity extent scorecard for each component going in to give us an element condition score. We had to then get that onto a cumulative probability of failure, and we use a power law for that. And then we can age it based on the different component rates of failure. This is done for every individual asset. And then we look at the probability of failure in the next year or the next 10 years. You can choose. And then we have to, that's for a component. The trust have to actually report to government the condition of the network. And they have to give a score put for each asset. So we use the criticality essentially to weight the components to get an asset condition score. And we can aggregate them up. And then also in the future by predicting how it's going to be in the future. That's really nice, because not only do we get it for a bridge from sort of foundations and the walls and the parapets, we can also start looking at linear assets and run along the asset and look at different kilometre lengths or the whole canal. And in fact, you could aggregate up to the whole of their system, the whole network, and get a single number. And we also use then, of course, the criticality, for monetized risk. So when we've got the cost of failure and the probability of failure, you can directly get a monetized risk, which is absolutely important for the interventions, which I come into now. So we can reduce the risk by doing interventions, replacement, refurbishments. And what we need to know from the experts is, well, how does that affect the condition? How does that change things, the probability of failure? And what are the costs of those interventions? So we actually do a bottom-up costing of the works. And then we wanted to provide a kind of a scheme of works that provides the best intervention strategy for that asset, for all the culverts or all the bridges. And we look at things like, well, what's the desirable, the things you really need to do, the essentials almost. Then the unconstrained, another scenario you can run is where money's no object, let's just do all the useful things. And they bookend your two polar opposites of what you could do in interventions. But normally your budget is not unlimited, it's never unlimited. So particularly budget constraint is important, where you then start to say, well, this is the money we've got, and maybe if things are bad, we have to reduce it because of unexpected costs elsewhere. So exploring what happens when we start reducing the budget, or we might want to work on, let's just constrain the risk. Let's maintain the risk in the system or reduce it by a certain amount. And the modeling can do all of that because we can just model all those interventions. And then we stick it. I've made a nice little tool for them. It actually runs on the cloud. It runs on Azure, and they've got a web app you can see there, and we can run this on our laptops, the web app. But very nice tool that all the people, all the asset leads can be using. I just sort of wanted to mention that this isn't an end of a journey. This cycle's still going on. As we start with 3, we've then gone up to 10 assets of different types, and we're still going through this and improving all the time. So.
So our brave new world. We've had to learn a whole load of terminology and vocabulary, which has been quite painful for some of our engineers, especially constantly being told that not to panic, they're on a journey, isn't necessarily that reassuring. I think the talk this morning on the Parthian shot, I think some of them felt that the bows and arrows were coming quite regularly. We didn't think we could do this, and I think we're still actually in a state of shock that we can. We didn't think we had the data. You know, we've got 200-year-old assets. Yes, we've got some nice drawings on parchment in cupboards somewhere, but we didn't have the breakdown data, the fault data. It's been a conscious decision that all those involved have to get to grips with the maths, including myself, which I found quite tough at times. Great patience on the behalf of decisionLab to keep talking us through what we're looking at. But the great thing is that there's a huge amount of subjectivity has now been taken out of our condition assessments. We're coming to the end of our first stage, and we now have strategies and models for 10 assets. The next phase is to start being able to cross-assess the information. So rather than just decide on what the next 10 culverts are that need replacing, what are the next 10 assets across the whole asset base? Historically, some assets have always got repaired above others. Culverts and embankments are always more of a risk to us than perhaps bridges. But the models are showing us some different answers, which is really exciting. So lots of other just quick wins that we've had. We've already reducing our inspection costs for culverts. We've realised we've been inspecting them far too much. We're now doing a considerable amount of inspection in digital form rather than wordy reports that nobody reads. We've cleaned up a huge amount of data. We're now collecting stuff we're actually using rather than collecting stuff we think we should know. And we've reviewed a lot of the drop-downs and things that we use. And for the first time, we're actually getting to grips with our linear assets. So our canal channel, our towpaths, our hedges are now as important to us as our bridges and locks. And the condition assessments of assets are already improving our engineers' knowledge and a huge reduction in subjectivity. For the first time, we're seeing a difference in risk between assets. We've been so hung up on spending the money and repairing them with yearly budgets that actually to be able to take a step back and understand the risk across the asset portfolio is really good. The asset lead's having to think about all the interventions, not just the big project work, but the day-to-day maintenance. For the first time, we've been able to look at parts of the assets in isolation. So to take culverts, for instance, they are broken down into 7 elements now, but actually it's the bit that goes under the canal that if it breaks causes us the problems. So to actually be able to look at just the barrel under the canal for all the culverts we have within the business is vast improvement and saves us a lot of time rather than saying that an asset is in poor condition, but it turns out that it's one of the less important elements. We have a corporate asset management strategy document, and the models are already allowing us to plan rather than react, and to give us an understanding of risk in carrying out and not carrying out pieces of work. We still need to better understand our reliability and serviceability, both what we are achieving at the moment and what we can realistically aspire to. But we do truly believe that bringing together OR best practice and engineering expertise has already started to improve and provide savings and clarity on the management requirements of our assets, and the basis for which we can show good stewardship of the nation's waterways. So it's already helping to prioritise £110 million worth of investment, and it's also providing a step change in understanding risk. The Trust would like to take this opportunity to thank decisionLab for their professionalism, expertise and patience in taking some, at times, very sceptical engineers on a journey that they didn't necessarily always want to go on to produce working, informative models that many within the Trust thought were going to be an impossible task.
Okay. Thank you. So if you know, this is one of the assets that are just in Lancaster, one of the Trust's assets.
Okay, thank you very much. Thank you very much, Ian and Sheena. Questions from the panel? Who's going first? John.
Thank you very much indeed for the interesting presentation. I was just wondering, you talked about some benefits toward the end there. Have you put a financial number on those benefits? And I guess linked to that, do you have a feel for how far your programme of work will be different as a result of this project than it would have been previously?
I don't think we can quantify yet. We're just at the start of being able to look cross-model. But it's going to be, we know it's going to be huge, the improvement. We've never been able to have a 3, 5 year, even 10-year programme, and it's really important with the fact that our grant only lasts for 15 years to actually prove that we're spending wisely, and this will actually prove why we're spending and what we're spending on.
Yeah, because we talked about this, it's hard to quantify how it was because it was so reactionary. But I guess what is your grant per year?
55.
55 million pounds. The worry is that could be lost if they don't have a system in place that shows that the trust is managing this the correct way.
We are responsible for about 2/3 of navigations across the country. The fear is that if they don't like the way we manage them, they could go to someone else. The upside of that is if they like the way we manage them, we will get others.
Okay, thank you. Alan?
So an excellent presentation, thank you for that. I'm interested in that fourth quadrant that you really didn't say very much about, the validation and the testing and the feedback.
There is data on, it is quite hard. What we do is the model gives us expected numbers of failures per year and things like that. So we can match that against the data because there is the kind of growth level of failure. So we can predict that. There's kind of to begin with, what the challenge is, we actually ask the engineers to almost pluck a number out of the air, and they get very uncomfortable with this. But what we do is then put that in the model and then flush it through the model and get predictions coming out, which they can go, well, that doesn't look right, and we adjust. But one of the main ones is we get the asset leads to take about 30 assets themselves and rank them in order. And then we tell the model to give its ranking, and we look at the correlation. That's where we found out the highway agency's work was getting a correlation of 0.4, 0.3. And there's a reason for that. I don't understand why they've done what they've done, but they have two measures. One is really optimistic and one is really pessimistic. And if you take the average, you do okay, but no one's comfortable with that. Our one gets a correlation of about 0.9, so it's a really close correlation. And we then do is ask the engineers, so why have you got that one much higher? And then they look at it, generally they look into it and realise the model has considered something they hadn't considered. They can sort of reverse engineer it. So that it's not a validation as we can just sort of do a plot and do a line and do that. But we can do kind of like an engineering peer review of the results and a post-analysis. And that's the kind of, so it's very much part of that loop as we then improve the model.
Okay, thank you. And a related one, I think, on sensitivity testing. So you've got lots of linkages effectively and assumptions going through that system in terms of how you build up to, let's call it figure of merit at the end. How much do you have to change some of those assumptions before you start to change the resulting strategies?
I would say there are thresholds in there, and they are currently quite the thing is, as long as you're consistent in your thresholding, because we're essentially at the moment really ranking, then it kind of doesn't matter so much. As long as you're consistent, it's the inconsistency. So there was concern that sometimes the engineers are so passionate they really want to set their thresholds low, thinking we've got to fix it if it's that level. And then the model starts saying you're going to have to spend £100 million. And that's really telling us that they're just being a bit too caring. That's not realistic, but that's just a threshold. But I think because the methodology is consistent in the components and then we're aggregating them, that we don't actually have that problem because the order doesn't change, even if we start changing those things. And it's quite systematic, like the costs. What is the cost going in? So it applies to all of those uncertainties. There are aims, because we kind of have a rule-based approach, because the bridges are 800 culverts. We don't cost the failure of individual culverts yet. What we do is say a culvert in an urban area, a big one of this length is going to be that much. And it kind of, we sort of cost things in the usage, so it kind of has rules. So it could be a bit sensitive to them, but there is aspirations that more data go in. But I think it's always ranking. It does work out. It's always relative to last year and the year before.
We always feel we don't have enough money. And actually some of the early intervention analysis we've done where we've tried to maintain risk over a 10-year period, so we start and end at the same, has actually shown that we need to repair 2 culverts a year. That's what we are doing at the moment. So it's quite nice that it's showing that what we're doing is a holding pattern. So that there is some validation coming in as we go through.
Okay, Sanya?
Thank you very much for excellent presentation. You talked about criticality in your presentation, to estimate criticality, and you explained how you calculated the total cost of failure, and you mentioned components, repair, safety, utility, environment, and so on. Who decided on the weights? I understand you weighted this in the weighted sum. Who decided on the weights?
So those numbers, I think 4 of them, we took that directly from what's done in electricity. So in that reference I said Kenai, so this is Ofgem and the distribution electric companies have come up with a scheme where they call it criticality, but it's the cost of failure essentially for each component. So you can cost up the cost of failure for every component. And they took those, so that the safety one is probability of death and then the cost of a death. They had 4, we added utility in. You could add reputation, so it's got flexibility to add more, as many as you want. But I think that was from, one of ours kind of captured that. The fact that we have a charge in there for if drivers have to go around the country because the bridge is closed. The trust doesn't pay that, but they feel their reputation would be damaged by people just really furious so they're having to drive around. So that's kind of costed in within that inconvenience factor. So, so that cost of failure so it's very common in electricity. I think sort of water as well, so the utilities industry. So we just took it wholesale, adapted it for this application. It's quite unique.
Yes,
And
we're trying to keep it consistent across all the different assets so that it is comparable, but obviously some assets don't cause you to inconvenience fish or motorists, but we're trying to keep that so that the utility, safety, environment, repair and replacement costs all have to be considered for each model.
So it was different to what the trust did. I think we talked about what it's done in other sectors, and then the trust adapted it to their needs, really. So
historically, we did look into consequence of failure, but it was always taking the worst one as the driver rather than aggregating them up and trying to put some monetary value to them.
And mathematically, we're not weighting them. It's much more involved in that, but it's effectively, it weights them. Because if we just weight them, we don't get a number that matches. So we kind of dimensionally have to do some other things. But it's effectively, it's weighting them. So more things which cost more to repair will have a bigger impact on that aggregated score. But it's not a simple weighting, or it's not a simple weighting, because that actually mathematically doesn't quite work. But that's the gist of it. Yeah.
Good to hear that. It's not simple weighted.
No, it's not simple. It's not. It's much more involved than that. Yeah. I can show you the equation if you're interested. But yeah.
Okay, I'm going to call it there unless you've got any further very quick things. No? Okay, right. So I'd just like the audience to please thank Ian and Sheena again for an excellent presentation.